Alright, in this video we're going to talk about logarithmic functions. Now what a logarithm is basically is an inverse of an exponential function. Right? So logarithms and exponentials are inverses of each other. They undo what the other one does. If you didn't watch the video that I did on inverse functions, you should probably check that out where I explain in more detail what inverse functions are. But an example of inverse functions are exponential functions and logarithmic functions. Right? So they undo each other. When we're trying to solve equations that involve exponentials or logarithms, we always use its inverse in order to solve it. So like if I have an exponential equation, I'm going to use logarithms to solve that equation. If I have a logarithmic equation, I'm going to use exponentials in order to solve that, right? Since they're inverses, then they undo each other, they cancel each other out, right? So the definition of a logarithmic function. The logarithmic function with base a, where a is greater than 0, so a is a positive number, but a is not equal to 1. Right? Just like if you didn't see the videos I did on exponential functions, the definition of an exponential function, the base of that exponential function also has to be a positive number not equal to 1. Since the logarithm is the inverse of the exponential, it has that same requirement that your your base number, has to be a positive number, but it cannot be equal to 1. Any other positive number is fine. All right, so the definition of a logarithm. And we abbreviate the word logarithm with just log for logarithm. So and we say log when we say this. We don't say logarithm. So log base a of x equals y is the same thing as saying a to the y power equals x. Right? So if you recall something about inverse functions, they switch the inputs and outputs. So if I have a logarithmic function here where x would be my input value and then y is my output, when I have that in the or that's equivalent to an exponential equation where the input and output get switched. So my base a raised to the y power, right, the output of that logarithmic function, is the input to my exponential function, and then the output of my exponential function, the x, is the input of my logarithmic function. Right? Since they're inverses, they switch input and output values, x and y values. That's literally the definition of inverse functions, and that's what's going on with logarithms and exponentials. Right? So and we'll do some examples down here where I kind of explain that in a little more detail. But that's the definition of a logarithmic function. So a logarithmic equation is really just, it means the same as an exponential equation, just written in a different form. Right? The log base a of x, you can think of that as the exponent to which you must raise the base a in order to get the number x. Right? So log base a of x, the a is my base, just like with the exponential equation, that a there, we call that the base of the exponent. For a logarithm, that a that's in the subscript is also called the base, right? So it's log base a of x. And what that's equal to is, well, I have that base a, I need to raise that to some power to have it equal x. The power that I have to raise it to is what that logarithm is equal to. Right? So a logarithm is like taking that exponential equation and writing it in terms of like trying to find the exponent. Right? If I know a to the y equals x, but I don't know what y is, well, y is equal to log base a of x. Right? Or another way, if you're given a logarithm, log base a of x, a raised to some power gives me x, I need to figure out what that power is. Right? And when you're switching between exponential and logarithmic equations, and any exponential equation can be written in logarithmic form, and any logarithmic equation can be written in exponential form. Right? You can always switch back and forth between those two forms, which is an important thing to be able to do because, like I said a couple minutes ago, when you're solving equations, you're using the inverse function, so you're switching back. If you have an exponential equation, you need to switch it into log form to solve it. If you have a log equation, you need to switch it to exponential form to solve it. All right, so the little shortcut way, or not really a shortcut, but a little trick to remember how to switch. If you have a logarithm, log base a of x, you start with the base a. All right, so the a over here is your base, raised to the power on the other side of the equal sign is going to equal whatever's next to the logarithm. So base a to the y power equals x, right? A to the y power equals x. Little circle is almost like a little circular thing. You start with the base, circle around to the other side of the equation, circle back, a to the y power equals x. All right, that's a little trick for switching between those two forms. All right, let's look at a couple examples where we actually, we're given a couple log equations. We want to write them in the exponential form, and then we have a couple exponential equations. We want to write those in the log form. All right, so the first one, log base 10 of 100,000 equals 5. All right, so if I want to write that in exponential form, I start with my base, 10, All right, so it's a base 10 raised to the power that's on the other side of the equal sign, so it's 10 to the 5th power equals, and then I kind of circle back around, and the number that's up here, the 100,000, right? So 10 to the 5th power equals 100,000. Log base 10 of 100,000 equals 5. These two equations are equivalent. They're saying the same thing. They're giving us the same relationship of those three numbers, the 10, the 5, and the 100,000. It's just they're written in different ways, right? This is the base raised to the power gives me this number. The log base 10 of 100,000, basically what that is, it's the base 10, and then the answer is 100,000, and then that equals the exponent. All right, so if I just had, let me take away this, let me do this just to show you. If I just had log base 2 of 8 equals, and I need to figure out what that's equal to, well, the way I think about it is, well, I start with a base 2, I have to raise that to some power to equal 8. Right, so 2 to some unknown power equals 8. So what power do I have to raise 2 to in order to make it 8? Well, 2 times 2 is 4. 4 times 2 again is 8. That's 3 2's I multiplied together. So log base 2 of 8 equals 3 because 2 to the 3rd power equals 8. Right, so when you have to figure out what a logarithm is equal to, that's the way you think about it. Whatever number's in the subscript, that's your base. You have to raise that base to some power to make it equal the number that's right up here. All right, so 2 raised to some power equals 8. That's the 3rd power. So log base 2 of 8 equals 3. And then when you write that in exponential form, 2 to the 3rd power equals 8. Right, the base raised to this power over here equals that number. Right, and with logarithms, sometimes the hardest thing about logarithms is just understanding what it says. Like when you see log base 2 of 8, like what is that even asking me? It's asking you to take this base 2, raise it to some power to equal 8. Figure out what that exponent is. Right, when you're trying to evaluate a logarithm, you're trying to figure out an exponent. All right. Now, a couple examples going the other way. 2 to the negative 3rd power equals 1/8. Right. So here we're given an exponential equation, and we want to write that in the logarithmic form. Well, notice the arrows up here. They go in both directions, so you can go one way and the other. These first two examples, we went from the log form into the exponential form, but we can just as easily take something in the exponential form and change it back to a log form. There's three elements here. Right. There's the base, there's the exponent, and then there's what it's equal to. Right, the a, the y, and the x. I just need to put all those in the right spot, and I got it. All right, so what's my base here? Well, my base is 2. Right, that's the number that's being raised to a power. So when I write my log, it's going to be a log with a base of 2. Right, the base of the logarithm, the number in the subscript, matches the base of your exponent, the number that's being raised to the power. All right, so log base 2, and now the exponent goes on the other side of the equal sign. And then what that base to the power equals is what goes here. That's what we call the argument of the log function. Right, so log base 2 of 1/8 equals negative 1/3. Right, that's the same thing as saying 2 to the negative 3rd power equals 1/8. And if you want to check it, doing that little circular thing I talked about, the base 2 raised to the power on the other side, negative 3 equals, circle back, it equals 1/8. All right, and the last one here, 5 to the r power equals s. Right, so this works with numbers like we had with these first three examples. It also works if we have variables thrown in there. Right, it's just the relationship, those three pieces, and putting each one in its proper spot. So this one, I have to change this to the log form, so it's going to be a log. The base of my log is the base of my exponent, which is the 5. Right, the exponent goes on the other side of the equal sign, and then what the base to the power equals, which is s in this case, is the argument of the log function. Right, that's the x, that's like the input value to the log function. Right, so log base 5 of s equals r is the same thing as saying 5 to the r power equals s. Right, and again, that little circular thing, the base 5, circle over here to the r power, circle back, equals s. All right, so that's switching between logarithmic form and exponential form back to logarithmic form. Remember, any one of these two equations, you can always switch to the other form just by knowing that little pattern of where those three pieces go. And it's a really important thing to be able to do for a lot of different types of problems that you end up doing. All right, so I'm going to pause the recording here and erase some of this stuff or maybe all of this stuff and then put up another example dealing with logarithms. All right, the examples I put up here, we're going to be evaluating logarithms, which means like we have log base 10 of 1,000, and we need to figure out what that's equal to. Now, I kind of mentioned this in that last example that I had up here on the bottom. That example really was just about switching between one form and the other. I couldn't help myself, though, like explaining how to actually evaluate that logarithm. I just get so excited when I start talking about logarithms. But this example here is all about just figuring out what this logarithm is equal to and how we actually do that. Right, so log base 10 of 1,000 equals. I need to figure out what that's equal to. Well, I don't know what it's equal to, so let's just say it equals x. Right, it equals something that I don't know, so I'll just name it a variable, which is x. All right, now if I change it into exponential form, right, the base 10 raised to the x power equals 1,000. All right, so again, but when I'm dealing with a logarithm, like I mentioned a couple minutes ago, I need to get from this base 10 to this number here, and I need to find the exponent that takes me from 10 to 1,000. Well, start multiplying tens, right? 10 to the first power obviously is 10. 10 times 10 is 100. That's 10 to the second power. 100 times 10 is 1,000. That would be 10 to the third power. So my x here equals 3. All right, 10 to the third power is what equals 1,000, and you can do that just by multiplying tens over and over again. Right? So what I would say then to actually give the answer to this question, log base 10 of 1,000, log base 10 of 1,000 equals 3. Because 10 to the third power equals 1,000. Right? Yeah, so when I'm evaluating a logarithm, I know my base number, I know the answer, I'm trying to find the exponent. What power do I raise 10 to get 1,000? That's what this logarithm is equal to. Right? So again, that's the key thing when you're working with logarithms is understanding what they actually mean. If you understand what they mean, it's just like I said, it's just working with exponential stuff a little bit backwards. Right? Rather than knowing 10 to the third power and figuring out what that's equal to, you know the base, you know what it's equal to, and you got to figure out the exponent. So it's almost like working backwards to just almost like solving an exponential equation. All right, what is that exponent that's going to make this equal 1,000? All right, the next one, log base 2 of 32. Well, once again, 2, my base of 2 raised to some power is going to equal 32, and I need to figure out what that power is. All right, so start multiplying 2's. 2 times 2 is 4, 4 times 2 again is 8, 8 times 2 is 16, 16 times 2 is 32, that's 5 2's I multiplied. So log base 2 of 32 equals 5 because 2 to the 5th power equals 32. Right, now when you're doing these problems, like your answer is 3 here, your answer is 5 there. Right, this other part, because 2 to the 5th power equals 32, you don't necessarily have to include that with your answers. I'm just putting it there so to make sure we understand why the answer is 5. All right, log base 2 of 32 equals 5 because when I take that base 2 and raise it to the 5th power, I end up with 32. All right, so that's that one there. Log base 10 of 0.1. All right, so if I have 10 raised to some power, that has to equal 0.1. Well, this one's going to be a little bit trickier because 0.1 is less than 10. All right, so if I start multiplying 10 times 10 times 10, I'm never going to get 0.1. Right? Now, a little trick to this, 0.1 is obviously that's in the decimal form. What is that as a fraction? Well, that 1 is in the 10th place, right? If you remember your place values, when you go to the right of the decimal point, there is no 1's place. There's the first one you get to is the 10th place. So since I have a 1 in the 10th place, that 0.1 is the fraction 1/10. Right? And if you don't remember that, go back and study your place value that you probably should have learned in like elementary school or early in middle school or something like that. But that 0.1 is the same as 1/10. Well, 10 raised to what power is going to give me 1/10? Well, that's going to be the -1 power, right? Because negative exponents, if I do 10 to the -1, that's 1 over 10 to the +1, which is 1/10, right? So logarithms, the answers to logarithms could sometimes be negative numbers, like in this case, right? 10 to the -1 is what's going to give me 1/10 or 0.1. Right? And knowing the rules of exponents is important when you're working with logarithms because logarithms and exponents are so closely related to each other. So if you got some of the laws of exponents, you might want to go back and review some of the videos I did on those laws of exponents because they come up all the time dealing with logarithms and exponential functions and things like that. All right, the last one here. Log base 16 of 4. So I have 16 raised to some power equals 4. Well, how do I get from 16 to 4? Well, I can take the square root of 16, right? The square root of 16 equals 4. But what exponent corresponds to the square root? Again, if you remember the laws of exponents, that's the square root is the 1/2 power. So log base 16 of 4 equals 1/2 because 16 to the 1/2 power equals 4. That actually went off the screen there a little bit. 16 to the 1/2 power equals 4, right? That's the square root of 16, which equals 4. All right, so that's a few examples of evaluating logarithms, even some tricky ones with negative and fraction results. But again, knowing the laws of exponents is really important when you're dealing with logarithms. So review those laws of exponents if you don't remember them that well.